Hello, my name is Thais, and in this video, I will try to explain a little bit about eBPF. Usually, operation systems have a kernel. The kernel is the heart of the operation system because it has full and unrestricted access to all hardware. The user space requests the kernel to perform privileged operations, like reading the storage disk, for example. Sometimes we want to add a new functionality into the kernel. To do it, we need to change the kernel code, or we can load a piece of code into the kernel. But why load code into the kernel? Full kernel access might be useful for dealing with security, networking, profiling, and etc. There are different use cases according to user necessities. Change the kernel code can be pretty complex because we need to recompile whenever we add a new functionality, and the kernel is hard to debug, and the kernel has different layers. The Linux kernel allows the user to extend its code using Linux kernel module, or LKM. LKM does not need to recompile the kernel code. It loads directly into the kernel. But it might be unsafe because it might crash the kernel as its code isn't checked. Think about it, they created the Extended Berkeley Packed Filter, or eBPF. What is eBPF? eBPF is a kernel technology of the Linux. It started in the version 4 of the kernel. It runs in boxed programs. In this way, it does not change the kernel code. It verifies the program to ensure the kernel security. How does eBPF work? eBPF is event-driven, and it is attached to a code path into the kernel. The program can be written in C or P4 language. If you use the C language, you should use a subset of the C library. The program can be compiled using LLVM compiler, and it can have only 4096 instructions. This limit is important to ensure that the program execution is finished into the kernel. There is a workaround called tail calls. You can put a call at the end of the program to call another eBPF program to continue the process. There are some toolchains that make the process of creating an eBPF program easier. The BCC or BPF compiler collection, for example, allows the user works with Python instead of C. Basically, you write an eBPF program and compile using LLVM compiler that generates an eBPF bytecode. You need to create another application in the user space to request the kernel to attach the eBPF program in some point. And this bytecode is checked by a verifier within the kernel. If the program is considered safe, then it runs in a JIT compiler. This program can do many different things. This program, for instance, can store some data in maps. And these maps can be accessed in the user space. There are some special functions called helpers that allow eBPF to perform a wide variety of tasks that make it more feature-rich. These helpers are predefined by the kernel and allow things like creating tail calls, generating random numbers, and manipulate maps to store data in a key value style. There are several types of maps that eBPF program can create. They differ by performance aspects, depending on the type of data that will be manipulated. A map can be shared between eBPF programs. eBPF programs are attached at hooks, also called triggers. Some examples of hooks are system calls that occur when the user space functions request the kernel to access privileged resources, network events that executes when a package is received, function entry and exit, and kernel probes, which are instructions inserted somewhere in the kernel to collect debugging and performance information. Some disadvantages of eBPF programs are it's restricted to Linux kernel, and eBPF increases security when it limits what the program can do into the kernel, and it also limits the power of the eBPF programs. Well, that's it. Thank you so much for your attention.